Buenas tardes. Les pido perdón, pero mi presentación se va en inglés. ¿Sí? First of all, I'd like to thank you for the opportunity to participate in this taller. And my name is Silvia, and I will talk about the experience of the CCST INPE in the estimation of land degradation in the Caatinga and Cerrado biomes in Brazil. Our INPE team working in the project Forest 2020 is formed by 6 members, and I will detail further their work in this presentation. To begin, I would like to give an overview about our institution and the center that we are working in Brazil. INPE means National Institute for Space Research, and it is a Brazilian institute dedicated to research and space exploration created in 1961. The institute has facilities in 12 cities, and its head office is located in the city of São José dos Campos, state of São Paulo, and it is where we work. The activities currently developed by INPE seek to demonstrate that the use of space science and technology can influence the quality of life of the Brazilian population and the development of the country. INPE has been working on 8 areas of research and development, being then space and atmospheric science, weather forecast and climate studies, engineering and space technology, Earth observation, satellite tracking and control, integration and test laboratory, associate laboratories, and Earth system science. This last activity is developed by the Earth Science Center, and this center works to expand scientific, technological, and institutional capacity of Brazil on global climate change. It has the aim to increase knowledge of this phenomenon, identify impacts on the country, and support public policy problems facing the national and international levels. The mission of the center is to generate interdisciplinary knowledge for national development with equity and reducing environmental impacts in Brazil, provide technical and scientific information quality to guide public policies for mitigation and adaptation to global environmental change. The CCST has a differential that when it brings together in a unique way in Brazil expertise and leadership in these areas of natural science, social, and modeling. The CCST organization is based in integrated components through cross-cutting projects aiming at the construction of sustainability scenarios for Brazil. It is working in 3 main lines of research, being then the first one, Earth system modeling and analysis, global Earth observation system, and diagnostics and scenarios of the Earth system. So after presenting a little bit of our context, institutional context, I will talk about the CCST experience in the estimation of land degradation in 2 Brazilian biomes. The first one is the Caatinga biome, and the second, the Cerrado biome. Talking a little bit about the Caatinga biome, this biome covers about 12% of the Brazilian territory, and it is located in the northeast Brazil. It occupies an area mostly coincident with the region called Brazilian semi-arid, which is described as the most populated and the most biodiverse semi-arid region in the world. Plant life in the Caatinga comprises scrub trees that remain dry and withered almost all year round. Caatinga vegetation ranges from the deciduous low shrub to small patches of tall dry forest, often fragmented. The climate in the Caatinga is hot, with long, dry seasons. Rainfall in this region is extremely irregular in both its temporal and geographical distribution. Usually more than 75% of the total annual rainfall occurs within 3 months. Here we have some pictures of the Caatinga biome, and we can see the sparse and spaced vegetation in pictures 2 and 3. Also, we can see in these pictures the rock outcrops. And another characteristic of this biome is that the layer soil is not very thick. The second biome is the Cerrado. It is the second largest biome in Brazil, covering about 2 million square kilometers. It represents almost 25% of all Brazil. The Cerrado has 2 distinct seasons, a dry winter and a rainy summer. And the rainy season is longer, around 6 to 7 months, and the overall amount of rain is higher with 800 to 2,000 millimeters per year. The typical Cerrado vegetation ranges from closed or open canopy deciduous and semi-deciduous forest with a maximum height of 15 meters to shrub to natural grasslands. Many types of fauna live in the Cerrado as well, including endangered species. Here we have the characteristics of the Cerrado, and we can see the diversity of landscapes and the different types of relief and vegetation. So, first, I will talk about the project related to the Caatinga biome developed in the CCST, called Early Warning System for Drought and Desertification. This project was developed in the Brazilian semi-arid region, and the motivation and context of this project was based on the northwest region of Brazil are facing its worst drought in 50 years, with more than 1,400 municipalities affected. We are talking about 10 million Brazilians affected by the drought in the northwest. The three main objectives of the Early Warning System project were monitoring the land degradation process and its spatial-temporal evolution, providing the tools for prevention and mitigation of drought phenomena to decision makers for a sustainable planning, and integrating and assimilating the biogeophysical and socioeconomic georeference data in several temporal and spatial scales. The Early Warning System was based on the Medalus project methodology, and it aimed to identify environmentally sensitive areas through a multifactorial analysis based on a general knowledge and location of active process. It was applied the sensitive index to desertification, and the SID equation encompasses 7 physical components, among them the land use and land cover change. So why is the land cover and land change why is the land use and land cover change important? It is because if an area is losing the vegetation and maintaining the bare soil for a long period, this area is more susceptible to erosion and degradation. In the context of the Early Warning System project, it was mapped the land use and land cover change for the Brazilian semi-arid region, and we can see here in this map that the agriculture class, represented by the red color, has increased over the time, the interval between 2000 and 2010, while the Cerrado class, represented by orange, had an omission along the time. And these two classes is located here in the west portion of the Brazilian territory and coincides with the Mato Piba region that I will present further in the second project. Considering this map, the Caatinga biome had its original vegetation reduced approximately 5% between 2000 and 2010. In this project, considering the Brazilian semi-arid region, we have also a small portion of the Cerrado biome, and this portion is represented by the bright green color in this map. Consider only this area, between 2000 and 2010, the Cerrado had its vegetal cover reduced about 16%. So, considering the vast experience of some INPE team members in the Caatinga biome, we started to work in the Forest 2020 project, and we will apply this methodology used in the Caatinga biome to the Cerrado biome, and I will explain a little bit more detailed this methodology soon. So, our INPE team is formed by the researcher Jean Ometo, who is the coordinator of the project. Alexandre is working in the change detection maps in degraded areas of the Mato Piba region. Rita is evaluating the forest fire risks in the Mato Piba region as well, and I will talk about these two activities in this presentation. The other team members are Fabricia, who is monitoring the deforestation in Jalapão conservation units over time. I will model the forest dynamic and agricultural land interface, considering the Brazilian legislation on forest conservation. and Heráclito is analyzing carbon flux in cropland expansion in the Brazilian Cerrado biome. So according to the change detection methodology, it is based on the extraction of information related to landscape monitoring. It is defined as the recognition of changes in the characteristic patterns of a given target in the image over a period of time. And the change detection technique used was based on the difference between vegetation index, and we use in our work the normalized difference vegetation index, NDVI. So to create the change detection maps in degraded areas for the Matopiba region, the methodology under development aims to identify areas of land degradation through constant NDVI monitoring that will allow the observation of areas devoid of vegetation and more vulnerable to soil erosion. Just to clarify here in the context of this project, we understand land degradation as the temporary or permanent decline in the productive capacity of the land. Previous studies recognize that areas with bare soil over a long period of time are a good proxy of degradation, considering that unprotected topsoils are susceptible to severe erosion. The early detection of degradation process is necessary to reduce and prevent the advance of degradation due to the indiscriminate exploitation of natural resources in developed countries of the world. Remote sensing products and geographic information systems provide seamless methods and tools to store and organize the information necessary for the development of monitoring and early warning systems of land degradation. So, multitemporal analysis of NDVI, which is being used in this work, data allow the detection of degradation trends based on the relationship between NDVI and biomass productive. For example, in areas where biomass productive is lower, NDVI values tend to be lower as well, indicating a large proportion of bare soil surface. So based on the frequency and persistence of bare soil, we proposed a degradation index to characterize the degradation extension and intensity during the study period in the Matopiba region. Talking a little bit about the study area, the Matopiba region is formed by 4 states, 3 partially, Maranhão, Piauí, and Bahia, and one totally, the Tocantins state. It is a Brazilian frontier with the much highest potential of grain cultivation. And it's formed by 3 biomes, 2 in a small portion, Amazonia and Caatinga biomes, and almost in its totality by the Cerrado biome. The total area of the Caatinga is nearly 735,000 square kilometers, which means the sum of Spain and the United Kingdom. In this area, we also have 5.4% of indigenous lands and 10.2% of conservation units. Considering the Matopiba region, it was selected 3 window areas to validate and calibrate the methodology during the field work. The first one was Balsas in Maranhão, because this area has a high potential index of grain production in the state. Formosa do Rio Preto has a lot of degraded areas, including the desertification zones, and Jalapão State Park in the Tocantins, it's an area without anthropic activities and some protection areas. These 2 areas here below are being studied by another group in Brazil, INPE, who is working on the Project Forest 2020 as well, and is mapping the land use and land cover change over the time. So for the first activity, considering the degraded areas model, the boxes in green represented the activities that has already been concluded. The step 2 in orange is being processing, and the validation and calibration of the activities will be done in July during the field work. And the step 3 will be done soon. And it will be employed the same methodology used in the step 1. However, for the step 1, the time interval considered is the year 2000 to 2017, and step 3 will encompass the interval 1985 to 1999. So for this first step, it was used more than 13,000 Landsat images for the entire period and 34 modes images for the year 2012, with a spatial resolution of 30 meters and 250 meters respectively. For the image processing and implementation of the algorithms, we used the Google Earth Engine platform and JavaScript and Python programming language. To calibrate the threshold value of any DVI for bare soil, both for the dry and wet seasons, it was necessary to compare the range of any DVI values for the different vegetation or land use. Here in this flowchart, we can see the three main processes involved to accomplish the step 1. The first process was the construction of any DVI mosaics for each season, dry and wet season. The dry season was formed by the months May to August, and the wet season was represented by the months January to March and October to December. So in these two pictures, we can see the same place in both seasons. And when you work with a methodology that needs to identify the degraded areas, it's really important to separate the both seasons to do not make mistakes when you are identifying these areas. For example, if you analyze only the dry season, you can map the highlighted area as degraded. And it's not degraded, it's just a seasonal response for vegetation if you look at the wet season picture. Also in the process 1, it was applied the cloud shadow filtering. And here we can see why this technique was employed. We have the mosaic of images for the year 2000 without filter and with the cloud shadow filter. If we use this, we can recover almost all the information to the selected study area. The process 2 was the classification of each pixel for value 1, bare soil, or 0, no bare soil, and the threshold for dry season and wet season were defined. For the Caatinga biome, it was defined the threshold 0.30 for the dry season and the 0.55 for the wet season. This threshold was applied for the Matopiba region as well, and it will be testing and calibrate the methodology during the field work. Here we can see an example of forest sample and bare soil sample used in the Caatinga project, and we'll do the same for the Matopiba region. The last process is regarding the degradation formula, and the degradation index considers the frequency and persistence of the exposed soil being assigned weights for the soil degradation that vary linearly between the first and the last analyzed year. The value of weight varies between 0, which indicates that the exposed soil did not remain for all analyzed years, and 1 indicates that the exposed soil data have exactly the same weight and remained throughout the analyzed series. Here we have some preliminary results for the Matopiba region, and the degradation index, the range of the degradation index were separated in two classes, the moderate degradation in yellow and the high degradation in red. Here, if we look at the moderate degradation, we can see that the high index was for the Tocantins state. However, when you look for the high degradation, the highest index was for the Piauí state. So it was presented the first activity that we are developing in the project. The second one is related to the risk of forest fires model. In this flowchart, we can see also the activities that will be employed in this process. and in green is the activity that we have already finished. At the moment, we are calculate weights for evidence for each independent variable, and the 3 other boxes in blue will be done soon in the project. So, the risk assessment of forest fires is based on the identification of the factors that influence fire regimes and that determine their spatial distribution. The model is being built upon machine learning techniques. The classification algorithm used is the naive Bayes, considering the Bayesian method of probability, and the implementation of the algorithm is also being done in the Python language. The burning frequency was selected as the dependent variable, and in this map, for example, considering the period 2013 to 2017, if an area burns in all of the years analyzed, we colored them by red. If there is no fire during this interval, the color assigned is green. So far, we have selected 12 independent variables that are being analyzed, and among them we have distance to roads, to settlements, to urban area, to railways, to ports, to rivers, and to indigenous lands. We also have days without rain for the dry period, altimetry, aspect, land use and land cover, and ray density. So with this, we have the 2 activities that are already being initiated, and we have the other 2 that will be initiated soon. Concerning them, as I said, we have the carbon flux, considering the interface soil, plant, and atmosphere, and the agriculture areas that are at odds with the Brazilian conservation laws. So thank you, and sorry, I'm really nervous. Thank you.
Sí, gracias, Silvia. Tenemos espacio para un par de preguntas. Todavía quisiera aprovechar que tengo el micrófono para hacer la pregunta. La voy a hacer en español y si no, a ver si en inglés. Ok. No recuerdo si el nivel de referencia de emisiones forestales de Brasil sometido ante la convención incluye degradación forestal. Creo que solo es deforestación. ¿Tú me puedes confirmar eso? Bueno, aquí Juan Pablo dice que solo incluye deforestación, ¿verdad? Ok, porque en todo caso mi pregunta era estos enfoques para determinar la degradación, es decir, este concepto de land degradation is wider que forest degradation, ¿no? Entonces pensé que tal vez había una relación entre estos con sus estimaciones de emisiones de su nivel de referencia nacional, pero no lo incluyen más bien, ¿no? It's not included. Ok, ¿más preguntas?
Sí, gracias. Felicidades. ¿Cómo han considerado el tema de la fenología para calcular la degradación utilizando el NDVI? Bueno, tomando en cuenta, hago la pregunta por el caso de Honduras, en el bosque seco, sería un poco difícil hacer estos cálculos, por ejemplo, cuando hay algún falta de lluvias, o las épocas secas o la época de lluvia. ¿Cómo han considerado esa parte?
Sí. My mind is like Portuguese, Spanish, and English. Can I answer in English, please? As I said, I'm presenting the work of my colleagues, and I think I have seen, like for the Amazon biome, it's more difficult to identify by remote sensing data the seasonality of the vegetation. Here, I think it was more clear because the Caatinga biome has just 3 months of rain along the year. So I think for this biome, it's a small, how can I say, green When a small portion of green appeared in the image, you can see that it's a seasonality responsible.